Hi. We're going to introduce, it's a very short video here. There's just one concept I want to introduce, and it's actually a rule that will be very, very important very soon in something that is called uh, Kirchhoff's voltage law. But we'll see that later. For now, ignore this, and we'll focus on what we mean by the electric potential in a circuit. Remember the analogy with mechanics. The electric potential is equivalent to is analog to the height of an object that moves in 3 dimensions. So let's say you have a hiker here walking along a mountainside, and for a while the hiker goes up and down and so on. If you follow the hiker for a closed loop, obviously by the time you come back here, the hiker is back at the same height. So what that tells us in terms of equations, well, I don't know the height here, it depends on where I put the origin, but it's clear that the sum of the change of heights as I go through a closed loop must be equal to zero. So what I mean by that is that if you go from here to here, you have, let's say, delta H positive. The hiker went up a little bit. From there to there, the hiker went down a little bit. So you have a negative delta H. Then from there to there, you have a large positive delta H. Then from there to there, you have a large negative delta H. And finally, from there to there, you have a positive delta H. Now, if you add all the delta H, you keep track of the signs. If you add all the delta H for the entire round trip, it's obvious that you get zero. The net delta H must be zero. It just tells you that you're back at the same point. So you must have the same height that you started from. Okay, so that's the very obvious statement in mechanics that as the hiker goes around a closed loop on the mountainside, the sum of the delta H must be zero. Okay, it turns out this applies to a circuit through this analogy between H and electric potential. Remember that electric potential is like H, but voltage is like delta H. The voltage is a difference of potential. So what we have for an electric circuit, as you go around a closed loop in a circuit, it can be any closed loop you choose. The sum of the delta V as you go around the loop must be equal to zero. Okay, and this is a very, very powerful statement. It will tell us, it will help us solving much more complicated circuits, but it's also a very, very good double check. When you solve a circuit, you can pick any loop you want, and you must check that when you add all the delta V's around the closed loop, you get zero. That's a very, very good test of whether you got the right currents and the right delta V's in your circuit. Before we use that, just a reminder, very important rule that you actually proved in one of the practice problems. But let me just remind you. Recall that uh, if you have a charge Q that moves between 2 points, if you multiply Q by the delta V, the potential at the final point minus the potential at the initial point, Q times delta V gives you the change of electric potential energy of the charge. Now we're going to focus on positive charges here, those fictitious positive charges, just to make things simpler. Um, so if Q is positive, now what happens when the charge goes to a resistor? A charge that goes to a resistor, whether it's positive or negative, always loses energy. That's energy that goes into heat or light. So when a charge, here I should have said a positive or negative charge, goes through a resistor, it loses potential energy, which means that delta U is negative. Now, if Q is positive now, okay, so delta U is negative. If we take Q is negative, then we have that for a positive charge, as a charge goes through a resistor, delta V must be negative also, right? Because Q is positive, so if delta U is negative, delta V is negative. So we must add this rule here, which is really important because that tells us the sign of a delta V as the charge goes through a resistor. Now, what does that mean really in practice? It means this. If you have a current that goes to a resistor, it means that as the charge goes through the resistor this way, the electric potential decreased, right? Delta V is negative. It means that here, this point is at higher potential than this point. And we indicate that by using the symbol plus and minus here. This is a bit misleading. This doesn't mean that the something is positive here and something is negative here. Uh, all those two symbols mean is that this point is at a higher potential than this point. That's all we mean by having a positive terminal here and a negative terminal here. So as the charge goes that way, we know that delta V is negative, so the potential must decrease. So the potential on the entering side is always at a higher value than the potential on the exiting side. So that's why we put a minus here and plus here. If the current goes this way, it's always the same thing. The current enters the side of higher potential and comes out on the side of lower potential. This is a general rule that would be very useful. Okay. Now, for an example of this, the rule for the delta V around a closed loop, let's go back to the circuit we saw before. So I have a circuit here with all the information given, all the resistance, R1, R5, R2, and so on, and all the currents are also given here, and the currents in those branches here. We also found, remember the directions. Current goes this way here, like that, like that, like that, like that, and like this. So that was our solution. Now, what I'm saying is that if we have the correct currents, we should be able to check that along any closed loop, the sum of the delta V must be equal to 0. Notice here, I've used the direction of the currents we found before to assign what we call that the polarities of the resistor. So which side is plus, which side is minus. For the battery, it's obvious. The long side of the battery is always the positive terminal, and this is the negative terminal. So that just tells us that on this side of the circuit, of the battery, this is at a higher potential than on this side. Okay, but for the resistors, we have to look at the direction of the current. Remember, the current always enters the plus side and comes out of the minus side. So I've used the direction of the currents to assign the polarities to all the resistors. The current here goes to the right, so this is the plus side, minus side. Again, what it means is that this side here is at a higher potential than this side. And I did that for all the resistors. Here, the current goes this way, so the plus side is here, the minus side is here, plus here, minus here, plus here, minus here. And going back to R1, I know this is plus and minus because the current here is flowing downward. Okay? Now, what I'm saying is that you pick any point you want in the circuit and then you go around the loop. Let's say we start here. If I go around a closed loop, I should have a sum of delta V equal to 0. For example, I go here, then I go through the battery. The potential here increases, right? I go from the minus side to the plus side as I go through the battery. So the potential increases by 12 volts. So delta V, as I go this way, delta V is plus 12. I keep going like this. I go here. Now I go from the positive side to the negative side. That means electric potential decreases. So it means the voltage, the delta V, is negative. So delta V, as I go from there to there, delta V is negative. Of course, if I had gone from right to left, it would have been a different sign, but we're going in that direction. Okay, it's negative, but what's the value? Well, for the value, I just use Ohm's law. I know the resistance, R5 is 4 ohms, and I know the current through R5 is written here. I5 is this. So I do 4 ohms times I5, I get delta V. But the key point is that the delta V I get will be a negative value. So I have a negative value here. Okay? And then I keep going like this. Now I have a choice. I can pick any path I want. Let's say we go this way. Then again, the potential decreases. I go from plus to minus. So delta V will be negative. What's the value of delta V? I take R4, 8 ohms, multiplied by I4, 0.25, 4 amps. So that gives me delta V, and it's negative. I go here. I have a choice. Let's choose to go left. So this time, as I go from this side to this side, the electric potential increases because I go from the negative side to the positive side. So as I go towards the left, the delta V must be positive. What's the value of delta V? You take R3, which is 12 ohms, multiplied by I3. I go here. Now I have a choice. I could actually go down and start backtracking my steps if I wanted to. There's nothing wrong with that. But let's go this way. Then delta V is negative. I go from higher potential to lower potential. What's the value of delta V? 7 ohms times I2. I go here. Let's choose to close the loop right away. So I go all the way here. And as I go here, the electric potential decreases. So delta V is negative. I go from positive to negative. It decreases by a value equal to 10 ohms times I1. So that will give you minus 7.12 volts. And I'm back to the initial point. When I add all the delta V's, I should get 0. And we get this. So this is the loop I just told you about. I go from there to there. I have a plus 12 volts. Then as I go through R5, I have a drop of 4 ohms times I5, and that's a drop of 2.848 volts through R5. Then as I go through R4, I have a drop again of 8 ohms times I4, and that gives a value equal to minus 2.032 volts. Then we went through R3. When we went to R3, the potential increased, right? Because when we went to R3, we went from the negative side to the positive side. So I had the gain of potential, so positive delta V equal to 12 ohms times I3. And turns out this gives 2.028 volts. Then we went through R2. Then there was a drop equal to 7 ohms times I2. It gives minus 2.03 volts. If we had kept more sig figs, this number here would have been exactly equal to 2.028, but that's okay. And then finally, we closed the loop and we went through R1. When we went through R1, we went from the positive side to the negative side. So we had the negative delta V equal to R1 times I1 minus 7.12 volts. And then we're back to initial point. If we add all those delta V's, we get a sum equal to minus 0.002 volts. Now, because we were working with 2 or 3 decimals, if you round that off to 2 decimals, you get 0 volts. And that's the good result. So you can play with that, pick any other path you want, go clockwise, counterclockwise, do anything you want. But if you go along a closed loop and you add all the delta V's, including the correct signs, you should always get something which is equal to 0. So that's a very, very useful double check of your currents when you've solved a circuit. And this rule that the delta V equal to 0 along a closed loop will play a very, very important role next week. Thank you.